18th International Physics Olympiad 1987 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Write me if interested. My email is fred1996@hotmail.com. Problem 1. Ascending moist air. Moist air is streaming adiabatically across a mountain range as indicated in the figure. Equal atmospheric pressures of 100 kilopascals are measured at meteorological stations M0 and M3 and a pressure of 70 kilopascals at station M2. The temperature of the air at M0 is 20 degrees Celsius. As the air is ascending, cloud formation sets in at 84.5 kilopascals. Consider a quantity of moist air ascending the mountain with a mass of 2,000 kilograms over each square meter. This moist air reaches the mountain ridge, station M2, after 1500 seconds. During that rise, an amount of 2.45 g of water per kilogram of air is precipitated as rain. Question 1. Determine temperature T1 at M1 where the cloud ceiling forms. Question 2. What is the height H1, at M1, above station M0 of the cloud ceiling assuming a linear decrease of atmospheric density? Question 3. What temperature T2 is measured at the ridge of the mountain range? Question 4. Determine the height of the water column, precipitation level, precipitated by the air, stream in 3 hours, assuming a homogeneous rainfall between points M1 and M2. Question 5. What temperature T3 is measured in the back of the mountain range at station M3? Discuss the state of the atmosphere at station M3 in comparison with that at station M0. Hints and data. The atmosphere is to be dealt with as an ideal gas. Influences of the water vapor on the specific heat capacity in the atmospheric density are to be neglected. The same applies to the temperature dependence of the specific latent heat of vaporization. The temperatures are to be determined to an accuracy of 1 Kelvin, the height of the cloud ceiling to an accuracy of 10 meters, and the precipitation level to an accuracy of 1 millimeter. Specific heat capacity of the atmosphere in the pertaining temperature range, Cp equals 1005 joule per kilogram per Kelvin. Atmospheric density for P0 and T0 at station M0 are ρ0 equals 1.189 kilograms per cubic meter. Specific latent heat of vaporization of the water within the volume of the cloud, Lv equals 2500 kilojoule per kilogram. Cp over Cv equals chi equals 1.4 and G equals 9.81 meters per second square. Problem 2. Electrons in a magnetic field. A beam of electrons emitted by a point source P enters the magnetic field vector B of a toroidal coil, toroid, in the direction of the lines of force. The angle of the aperture of the beam 2 by alpha 0 is assumed to be small, 2 by alpha 0 much less than 1. The injection of the electrons occurs on the mean radius r of the toroid with acceleration voltage v0. Neglect any interaction between the electrons. The magnitude of vector B, is assumed to be constant. Question 1. To guide the electron in the toroidal field, a homogeneous magnetic deflection field vector B1 is required. Calculate B1 for an electron moving on a circular orbit of radius r in the torus. Question 2. Determine the value of vector B which gives for focusing points separated by pi over 2 as indicated in the diagram. Note, when considering the electron paths you may disregard the curvature of the magnetic field. Question 3. The electron beam cannot stay in the toroid without a deflection field B1, but will leave it, with a systematic motion, drift, perpendicular to the plane of the toroid. Part A. Show that the radial deviation of the electrons from the injection radius is finite. Part B. Determine the direction of the drift velocity. Note, the angle of aperture of the electron beam can be neglected. Use the laws of conservation of energy and of angular momentum. Given data, charge E over mass m is 1.76 by 10 power 11 coulomb by kilogram, V0 equals 3 kilovolt, R equals 50 millimeters. Problem 3. Infinite LC grid. When sine waves propagate in an infinite LC grid, see the figure, the phase of the AC voltage across two successive capacitors differs by phi. Question A. Determine how phi depends on omega, L and C. Omega is the angular frequency of the sine wave. Question B. Determine the velocity of propagation of the waves if the length of each unit is L. Question C. State under what conditions the propagation velocity of the waves is almost independent of omega. Determine the velocity. In this case. Question D. Suggest a simple mechanical model which is an analog to the above circuit and derive equations which establish the validity of your model. Formulae. Cosine alpha minus cosine beta equal -2 sine alpha plus beta over 2 multiplied by sine alpha minus beta over 2. Sine alpha minus sine beta equal 2 cosine alpha plus beta over 2 multiplied by sine alpha minus beta over 2.